So in data and signals of the discussion, we have covered various aspects. Now we'll see the transmission impairment. Transmission impairment means the problems in the transmission, whether it may be your analog transmission or your digital transmission. So signal, they travel through medium, that is transmission medium. You know there are two types of transmission medium, guided and unguided. So which are not perfect, and the imperfection causes this signal impairment, or you can say in simple word signal loss. So this means the signal which is at the beginning of the medium which is sent is not similar or same as the signal which is received at the end, or the receiver. So what is sent may not be received as it is. So there are various causes of impairments, and the most important are, this can be due to attenuation, distortion, or noise. So we'll see about attenuation, distortion, and noise. So these are the causes of the impairment: attenuation, distortion, and noise. You have to remember these three. So what attenuation means is, we are sending from point 1 the signal, and from this point to this point, the signal, as you see, the amplitude or the distance of from the original line, we call it amplitude only. But just for a new person, see the distance from this axis is what here, and we'll see what we get at point 2. At point 2, all these amplitudes have gone down. So this is just because the energy has gone down, and because of this we call that at point 2 the signal is attenuated. Then we can apply an amplifier, that is a regenerator, which will amplify our signal, and we can get what we have actually sent through the amplifier. So it will reboost or boost the signals. For example, suppose a signal travels through a transmission medium and its power is reduced to 1/2. That means first it was P1 or P, then it became P1 by 2. This means that the P2 is half of P1. That is P1 is nothing but P1 by 2, which we have written here. So the attenuation or loss of power can be calculated as, let us calculate it as dB. You know what dB is? dB is for decibel. Decibel is not a unit. Please understand that. Decibel is not the unit. It is just the power level, or you can represent these power levels, and this is given in the logarithmic form. So ratio of power level is given in dB, and you can also represent the gain and losses also in dB. That will be, say, some dBW or dBm. This is always capital dBm. This is the dB or the power level with respect to 1 watt. This is the power level with respect to 1 milliwatt. So dB is only helping you to reduce that complication of computation, because we'll get power of 10 minus 3, 10 minus 6, 10 minus more than that, 10 minus 9. So how to solve these? So we can represent these power levels in terms of dB, and you know, when we are using log, rather than doing multiplication of this sort, we can just add in log and subtract. So dB helps in reducing our computation. dB is decibel, which is the representation of power ratio. It is a ratio of powers. You can express the gain and losses also like this. So this is computed like this: 10 log. This is the power P2 by P1. Okay, if it is gain, loss can be given by P1 by P2. So we have 10 log 10 P2 by P1. P2 P1 can be in its own form, like in megawatt, kilowatt, etc. But when we change it, or we want to change it into dB, we use this formula inside this, because this is just a ratio. So our, say, watt by watt, it will be cancelled, or say milliwatt by watt, we can convert this milliwatt into watt and cancel. So this is a dB is a value which has no unit. dB has no unit. dB is just a power level. So this is 10 log 10 P2 by P1. We know that P2 is what? P1 by 2, that is 0.5 P1, and this is just 10 log 10.5, and that will be equal to 10 into minus 0.3, so minus 3 dB. So this is the loss of power attenuation. Now a signal travels through an amplifier and its power is increased by 10 times. So now the initial power is P1, the received power or the gain is 10 times of P1. So now we can calculate it in dB, like 10 log 10 P2 by P1, and P2 is nothing but 10 P1. These gets cancelled, and this is just 10 log 10. The base is 10, so it will be just 1. So that will be 10 dB. So see, the power increases by 10 times, but it will be just dB enhancement or gain of power. This is the gain. Now, why we use this decibel? Why the engineers use decibel? To measure the changes in the strength of signal, is that decibel numbers can be now added or subtracted. Once you go with the go to the logarithmic computation. Logarithmic in this you don't have multiplication and addition. You can easily add and multiply, add and subtract. So you can add or subtract when we are measuring several points, that is cascading instead of just two. So we'll see here in this figure. This is 0.1. This is 0.2, 0.3, 0.4. So 0.1 to 0.2 there is a loss of minus 3 dB. From 0.2 to 0.3 because there is an amplifier, so there is a gain of 7 dB. And from 0.3 to 0.4 again there is a loss of 3 dB or inverse gain, you can say. So what is happening here is, we saw that minus 3 first one, 7 was gain and minus 3. You can just easily add and you can say that there is a gain of 1 dB. So here we have a gain of 1 dB. That is why we use decibels. Sometimes the decibel is used to measure signal power also in milliwatts. That is what I indicated, it is given by dBm. dBm is nothing but in 10 log base 10 P by P, P1 by P2. This P2 is nothing but the milliwatt. So the power or the measure of power with respect to milliwatt, the denominator is milliwatt, or with respect to the ratio, the denominator is milliwatt. Okay, then we represent this as dBm, or you can easily write dBmW, but we are lazy, we'll write only dBm, and this is calculated by 10 log 10 pm. Only you can easily place the value here, where this pm should be in milliwatts. So you can easily calculate by this formula. So we can calculate the power of signal with the dBm minus 30, that is 10 log 10, and pm you can directly write here, because you know that the first one is minus 30 and the next one, this is milliwatt, and the denominator is also 1 milliwatt. So this is, we don't have to write this 1 milliwatt here. Otherwise this is obvious, this is 1 milliwatt in the denominator. But this becomes minus 30, and we can compute this power pm, because we know that 10 log pm, it is given that the power in dB is minus 3. So how can you compute this power? Will be 10 to the power minus 3 milliwatt. I'll tell you one more very good way. When you want to convert the dB into milliwatt, dBm into milliwatt, so what you have to do, you just take 10 and whatever is the value in dB, raised to the power minus 30 by 10. So that will be equal to minus 10 minus 3, and you can directly calculate. You don't have to use this formula. Just raise 10 to the power of whatever is here and divide it by 10. So minus 30 by 10 is minus 3. 10 to the power minus 3 is the answer in the milliwatts. We'll take one more example. The loss in a cable is usually defined in decibels per kilometer, dB by kilometer. This is loss. If the signal at the beginning of a cable is 0.3 dB by kilometer and has a power of 2 milliwatt, what is the power of the signal at 5 kilometer? So can you, the explanation we had, can you try to solve this question with the explanation we did just now? Let me tell you. The loss in the cable in decibel is what? Means I am asking a WHA at what? Is what? It is given that we have the signal at the beginning of the cable with minus 0.3 dB per kilometer. So you can just, because this is dB per kilometer, you have 5 kilometer, just multiply minus 0.3 dB by kilometer with 5 kilometer. So kilometer into kilometer will be cancelled. This will be in dB. So you'll get the loss in the cable for this 5 kilometer as minus 1.5 dB. Now we have to calculate the power, and I told you already how to compute the power. This is very easy because you know that this P1, the power is 2 milliwatt. Okay, in the beginning the power was 2 milliwatt, but we don't know what will be the P2. So we use this formula 10 log 10 by P2 by P1, and this is equal to minus 1.5. This is in dB. So now by rearranging, taking power, and we can find out the P2. I hope that you understand this. This will be 1.4 milliwatt. Then we talk about the distortion. That is distortion. It means that the signal changes its form or shape. Distortion means if this is a signal, it may be converted like this. So it changes its form or shape. This is at the sender. This is a composite signal send, and this is a composite of these three signals components in phase. But when you receive it, the components are out of phase. Means the composite signal received may be something like this at the receiver. This is distortion. Okay, I hope you understood this distortion. This is the change in shape. Now we come to the other one, that is noise. So we have a transmitter here, point 1. Here is a noise. Okay, we have a noise of the transmission medium. This noise can be thermal noise, it can be impulse noise. So there are 4 types of noise. When this noise gets added to this transmitter, the received signal could be like this. So it is somewhat changed. Of course, this noise has been added. So let us take an example. If power of a signal is 10 milliwatt and the power of the noise is 1 microwatt, what are the values of SNR or SNR dB? SNR is signal to noise ratio. Signal to noise ratio. So it only says that what is the strength of signal with respect to the noise, or how much signal is more than the noise. This is signal to noise ratio. So we need SNR to be high because we want the signal value to be higher than the noise. So SNR gives like this. We'll learn about the Nyquist and Shannon theory also, because Shannon theory adds up this noise. So it is given by 1 plus SNR, and then you have log here, and then B also, that is the bandwidth. So we'll see. Don't worry about this formula. We'll be covering it in the detail. But now we have a power signal 10 milliwatt, and the power of noise signal is 1 microwatt. So what is signal to noise ratio? This is noise and signal. Just divide these two. You will get the answer. Okay. How you are going to divide? You have to take the signal which was our 10 milliwatt, and you convert it into the microwatt. How you are going to convert it? You just multiply by 10 to the power 3. That will be micro. 1 milliwatt is already there. This one. So signal should be here. Noise should be here. So you can convert. I'm not saying that you convert micro into milli into micro or micro into milli. It depends on you. You know the differences. You know how they are converted. Milli is 10 to the power minus 3. Milli is 10 to the power minus 3 watt. Micro is 10 to the power 6 watt. Okay. So you just convert it, and the SNR will be 10,000. But you know how to compute this value convert this into decibel. 10 log 10. 10,000, that is 10 to the power 4, and that will be 40 dB. We have another thing, the value of SNR and SNR dB for a noiseless channel. This will be given by, because there is no noise, this is 0. So signal to power, there will be no noise, so we'll take it 0. So it will become SNR, signal to noise ratio is infinite, or you can find it in dB also. This will also come as infinite. So we can never achieve this ratio in real life. So it is an ideal value. In this figure, you can see 2 cases of SNR. That is a large SNR or a high SNR, signal to noise ratio, and this is a small SNR, the small signal to noise ratio. So this is a signal and you have a noise. When you combine them, you will get a large SNR. Okay, and you really require a high SNR. That means, because SNR is signal to noise ratio only. Noise, if it is less, then you can get as high. So you want it. What about small SNR, signal to noise ratio? This is signal and this is noise. So noise is greater than the signal. Here noise is smaller than the signal. So signal is higher than noise. That is why you are getting large SNR. While in this, the signal is small and noise is also small, or you can say noise is greater than signal. So you'll get a small signal to noise ratio. Now we come to data rate limits. In this we'll talk about the capacities also. So a very important consideration in the data communication is how fast we can send data in bits per second. And I am aware that you understand that Whenever we are talking about data communication, we talk in terms of bits per second. Bits per second, not bytes. Bytes is for the memory, computer memory, or various memories or a channel. So data rate depends on three main factors. First is your bandwidth, the level of the signal we use. As we know, 0, 1 and 0, 1, 1, 0, you already know that these are the levels. The quality of the channel, that is the level of noise. So noise also we have seen. So we'll see the noiseless channel, Nyquist bitrate. Nyquist is for the noiseless channel. Shannon came up with a improved version of Nyquist bitrate. It is for the noisy channel, and we'll be using both limits. So noiseless channel, which is not in the actual scenario, but it gives you a very good idea of the bitrate. So Nyquist bitrate is given by 2 into bandwidth, that is 2b log the base is 2 L. This is the formula, and these are the. I'll tell you what L is. We'll take examples also because this is important. So 2 into b into log. These are the levels. So bitrate is given by because bitrate is given by this formula, and this is the noiseless channel form. So increasing the level of a signal, as we saw that this is L, which is the level. So increasing the level of a signal may reduce the reliability of the system. You can increase the level, no problem, because if you increase the level, you'll get values that are higher, which is the bitrate. So bitrate will be higher, of course, if you have higher levels. But if you improve the levels or if you increase the level, the reliability or the errors will be higher. Let us take the submission that does the Nyquist theorem bit rate agree with the intuitive bit rate described in baseband transmission? They may match when we have only two levels. We said in baseband transmission the bit rate is 2 times the bandwidth if we use only the first harmonic in the worst case. However, the Nyquist formula is more general than what we have derived intuitively. So it can be applied to baseband transmission and modulation. And also it can be applied when we have 2 or more levels of signals. So we can consider a noiseless channel with a bandwidth of say 3000 Hertz transmitting a signal with two signal levels. So the maximum bit rate can be calculated as by Nyquist relation 2 into bandwidth log base is 2, and these are the levels. How many levels are there? How many levels? There are 2 signal levels. So we'll place 2 here. And what will be the frequency? See, the frequency or the bandwidth, sorry. The bandwidth should always be in Hertz. In this formula, bandwidth is in Hertz. So 2 bandwidth in log 2 of 2, this is 1 only. So you'll get 6000 BPS, B is small, BPS, bits per second. Consider the same noiseless channel transmitting a signal with 4 signal levels. So you have 4 here. L will be 4. So that will be maximum bit rate will increase dramatically from 6000 to 12,000 BPS, bit per second. So we need to send 265 kbps, kilobits per second, over a noiseless channel. That means we are going to use the Nyquist relation with a bandwidth of 20 kilohertz. So you have bandwidth also. How many signal levels do we need? So this is quite easy. You need to send 265. So 265 will be here, and you know by the Nyquist relationship that will be B and log 2, and here will be what? Levels. So you can easily compute by 265. This is kbps, so you have to convert it into kilo to be bps. 265,000 is equal to 2 into, and 20,000 you have to convert it into hertz. So 20,000 into log base 2l. So level can be computed by 2 to the power 6.625, that is 98.7 levels. So since there is this result is not a power of 2, this is not a power of 2. Is it a power? The nearest of power of 2 is 128, right? Or on the downside, this is 64. So this is not a power of 2. We need to either increase the number of levels or reduce the bit rate. So if we have 128, which is here levels, the bit rate will be 280 kbps. So if we have 64 levels, the bit rate will be 240 kbps. Now we see the noisy channel with Shannon capacity. We have seen the capacity because we have just noted the Nyquist capacity has given us the maximum bit rate. It has given us the maximum bit rate. But Shannon capacity, the capacity of the channel, is given by Shannon, noisy for the noisy channel. So we have to see this formula that this is nothing but the bandwidth into log, the base is 2, and this is 1 plus SNR. You know SNR, what is now SNR? Signal to noise ratio. So in this case, let us see that consider an extremely noisy channel in which the value of the signal to noise ratio SNR is almost 0. So SNR is 0 here. In other words, the noise is so strong that the signal is faint. Noise is too much. So for this channel, the capacity is calculated by V log base 2 1 plus SNR. And this is calculated by because this is 0, so 1 plus 0, and because this is log, log of 1 is 0. So the capacity will become 0. What it means is that the capacity of the channel is 0 regardless of the bandwidth, whatever be the bandwidth. So it is not dependent on the bandwidth. So we cannot receive any data through this channel if the noise is very high. We can calculate the theoretical highest bit rate of a regular telephone line. Let us see that how we can do that. Say a telephone line normally has a bandwidth of 3000, and this 3000 is in hertz. 3000 is the bandwidth. So the SNR ratio is usually what? 3162. This is 3162. So we place it in the Shannon formula, B log 2 of 1 plus SNR. This is given by 3000 log 2 3163. This is 34 kbps, around 34 kbps. So this means that the highest bit rate of a telephone line is 34.86 kbps. So if you want to send data faster than this, we can either increase the bandwidth of the line, or we improve the signal to noise ratio. These are the two options for you. The signal to noise ratio SNR is often given in decibels. So SNR is given as 36 and the channel capacity is 2 megahertz. So how we can calculate the theoretical channel capacity? This can be computed by, SNR dB is given by 10 log 10 SNR. So SNR will be what? I told you that you easily get it by, this is SNR 36. Okay. So how can you compute? This is so easy. You can compute it by take 10 to the power of, what is the value? 36, and just divide it by 10. So that will be 10 to the power 3.6. You will get it in normal value, that is if it is in dB. So now we know that the channel capacity, we want to know the channel capacity. We have computed the SNR, just place it here. That will be 2 into, this is 2 megahertz, so 2 into 10 to the power 6 log 2, and this value will place here. That will be 24 megabits. Okay, I hope you got the idea. This is very simple. Then the practical aspect. For practical purposes, when the SNR is very high, we can assume that SNR plus 1 is almost same as the SNR. So we don't have to do 1 plus SNR. So in these cases, the theoretical channel capacity can be simplified to C is equal to B into SNR in dB by 3. And we can calculate the theoretical capacity in the previous example by just placing 2 megahertz by 36 by 3. That is 24 Mbps. We have a channel with say 1 megahertz bandwidth. This is the B. The SNR for this channel is signal to noise ratio 63. What is the appropriate bit rate or signal level? We'll use this channel formula. B log to 1 plus SNR. B is 10 to the power 6. SNR is given as to be 63. So this is 64 to 2 to the power, it will be 6. So that will be 6 into 10 to the power 6. That is 6 megabit per second. This 10 to the power 6 is for mega. Then the Shannon formula gives us this 6 Mbps now, and the upper limit. So for better performance, we choose something lower, that is say 4 Mbps for example. So now we can use the Nyquist formula to find the number of signal levels. How you can compute? You know that 4 Mbps is the bit rate. We choose it like this. That will be equal to 2 into B log base 2L. This is 1 megahertz. As we saw that we have 1 megahertz as the bandwidth, and L can be computed like 4. So the Shannon capacity gives us the upper limit, and the Nyquist formula tells us how many signal levels we need. Signal capacity gives us the upper limit of the bit rate, that is 6 Mbps we saw, and signal levels, as we saw how many signal levels we need. So Nyquist gives us that. So this is one more part of the data and signals. I will be taking one more part that will be short. So thank you so much. Take care.